In the previous lecture, we introduced the important concepts of upper bounds, lower bounds, supremum, and infimum. We saw that some sets have a least upper bound property and greatest lower bound property. But an important question remains: in what kind of sets do these objects actually exist? To answer that question, we need the concept of an ordered set and the least upper bound property. That will be our topic in this lecture today. To define an ordered set, we first define what we mean by an order. The first property is called trichotomy. Whenever we take two elements of the set, exactly one of the three possibilities occur. Either the first is smaller or the second is smaller or both are equal. The second property is transitivity. If x is less than y and y is less than z, then x must be less than z. This guarantees consistency in the ordering. Once a set is equipped with a relation satisfying trichotomy and transitivity, we call it an ordered set. Here is the definition. A set S together with an ordered relation less than is called an ordered set. We also use the familiar symbols greater than, less than, or equal to, and greater than or equal to. The key feature is comparability. Given any two elements, we can always determine which one is smaller or whether they are equal. The most important example for order set is set of real numbers. We know that 2 is less than 5 and 5 is less than 8. Therefore, 2 is less than 8. This is transitivity. Similarly, any two real numbers satisfy trichotomy. Therefore, the real numbers form an ordered set. Now, we come to one of the most important properties in real analysis. An ordered set is said to have the least upper bound property if every non-empty subset of S that is bounded above has a supremum in S. The real number system possesses the least upper bound property. This property distinguishes the real number from the rational numbers. This theorem is one of the most important consequences of the least upper bound property. Consider all lower bounds of the set B. Collect them into a new set L. Since L is the set of all lower bounds, it turns out that L is bounded above. Therefore, L has a supremum. The theorem states that this supremum is exactly the infimum of B. Therefore, every non-empty set bounded below possesses an infimum. Let us understand the proof clearly. Every lower bound must lie below every element of B. So, every element of B acts as an upper bound of L. Since L is bounded above, it must possess as a supremum. That supremum is the largest among all lower bounds. In other words, it is exactly the infimum of B. Walter Rudin, in his book, explains why the rational number fails. Let us consider the set A, which is equal to set of all x belong to rationals such that x square is less than 2, and set B is set of all x such that x belong to rationals where x square is greater than 2. The elements of B serve as upper bounds for A. However, there is no smallest rational number whose square exceeds 2. Therefore, A has no least upper bound in the rational numbers. Hence, rationals does not have the least upper bound property. A common misconception is that the supremum must belong to the set. In the first example, that is E1 is equal to set of all R belong to Q such that R is less than 0. The supremum of this set is 0, but 0 does not belong to the set. You can see this second example. The same supremum belongs to the set here, as we have set E2 is equal to set of all R belong to Q such that R is less than or equal to 0. Supremum of this set is 0 and 0 belongs to the set. So a supremum may or may not be an element of the set. Consider the set consisting of all numbers 1 by n. This example we have mentioned in the previous lecture also. The largest element is 1, hence the supremum is 1 and it belongs to the set. The infimum is 0 because the terms get closer and closer to 0. However, 0 never appears in the set. This example shows that supremum and infimum may or may not belong to the set. In this lecture, we introduced ordered sets and least upper bound property. We also proved that the least upper bound property guarantees the existence of infimum. In the next lecture, we shall begin studying the algebraic and order properties of the real number system that form the foundation of real numbers. If this lecture helped you understand ordered sets and the least upper bound property, do support the channel by liking the video and sharing it with your friends. Subscribe to Higher Mathematics by Sri Vidya and join me in this complete real analysis course.